Capacity by itself is a very wide term. Someone says that he has a very good capacity. You never know what type of capacity he is talking about. It might be the capacity of jumping, capacity of learning, capacity of singing. So, capacity is a relative term. Whenever you speak of capacity, you must quote down what type of capacity. Like here, we are studying electrical capacity. What it means is the storage of electric charge, capacity of storing the electric charge. When you give the charge to a conductor, the potential on itself increase. The two would be directly proportional. The constant that we apply here is known as electrical capacity. Its unit is farad. Farad, a quite big unit. Farad. You see, the reciprocal of capacitance is also known as elastance. Its unit is quite reciprocal of farad. This is not very common, but you must remember that of capacitance, the unit is farad, that of elastance, that is reciprocal of capacitance, its unit is daraf. Q and V will be having a straight line graph. Q equal to CV. When we define potential, we simply use a definition which involves infinity. And work is something to do while finding the potential. Here also, when you are giving the charge, the area enclosed between this graph and potential axis will be equal to work done, that is half QV. This will be stored in the conductor that has been charged as electropotential energy. It will be known as electropotential energy. U, that's half QV. But sometimes we use the source of charge, the potential difference of which is not going to change. For example, if you charge a conductor with the help of a battery or the cell, the EMF or the potential difference of the cell is not going to be affected. So, in that case, you'll be having the graph between Q and V like this. Means potential is not changing and it is supplying the charge. In that case, this area is going to be QV. That means you could say the work done by the cell or the source in charging the conductor was equal to Q into V. That the energy stored in the conductor was half QV. What does it conclude? It simply indicates that in the process of charging, there is loss of 50% of the total energy supplied by the cell. Means only 50% of the energy supplied by the source is stored in the form of electropotential energy. For this very term, you see, half QV, we have another similar terms also, U, that is half QV, that is half CV square, that is half Q square upon C. So, you have three methods, three types of procedure to show the term for electropotential energy. That's your choice. You might use any of the three depending on the situation. These are the terms. We'll consider one isolated sphere. Isolated sphere, suppose the radius is capital R. For this, radius is capital R. And you give the charge Q. In that case, the potential will be given by this, the formula we know for potential of a sphere. Q upon V, that is C. So that way we get the formula for capacity of isolated sphere, this thing. This is the formula in SI. And you know, when it comes to CGS system, 1 upon 4 pi epsilon naught has the value 1. So, in CGS system, this is going to be radius. So, if you study in some numerical problem that capacity of a sphere is 4 centimeter, it's not wrong. Actually, you are giving here the capacity in terms of radius itself. Means capacity may be quoted in terms of radius of any sphere when you are dealing with CGS system. So that is how we find this. This is capacity. Now, if there are two conductors might be having any radius and they are having the values Q1, C1, R1, Q2, C2, R2, they are joined together like this. So, total charge that they had initially will be equal to the sum of the final charges over them finally. Capacity is not going to change by just connecting them. And charge always flows from higher potential to lower potential. The size is not material, the amount of charge is not material. Only the thing to decide the flow of charge is the potential. It flows from higher to lower potential. So, unless the potential becomes common, the charge is going to flow continuously till the potential is common for both, and this will be given by the total charge upon total capacity. It's going to be Q1 plus Q2 upon C1 plus C2. You can put the value C1 V1 C2 V2, you get this relation. If you compare the ratio of the two final charges on them, that will come out to be direct ratio of their capacity. Obviously, their potential changed. The higher has gone lower and the lower potential has gone little higher. The potential will change for both. Their potential, this is very interesting, their potential will change in the inverse ratio of capacity. Why have I introduced here minus sign? Because once potential of one conductor will increase and the potential of the other conductor is bound to decrease, only then they can have common potential. So, when you talk of the ratio of charges, it is plus C1 by C2. When you talk of the ratio of change in potential in the conductors, it's going to be minus, indicating that they change oppositely. Finally, we'll now see how the drops combine or merge, or how a big drop is split into many small drops. Here I have chosen the consideration of merger of small drops. You see how smart drops have been shown here, how fantastically they have been represented, and they have combined to form a big drop. The big drop, mass is always conserved. Suppose there are n drops and they have formed a big drop. They had the radius r, and now suppose the radius that a big drop has become r dash. Volume is 4 by 3 pi r cube, that of a single drop, that is of spherical shape. When they combine, it's going to be 4 by 3 pi r cube, the volume of one big drop. Volume will remain conserved. Or even if you want to stretch it more, you could say, you could start from here, that mass will be conserved. You multiply both sides by the density, it will get cancelled, and ultimately what is left is the conservation of volume here. So 4 by 3 pi gets cancelled and you get this relation. I have chosen a small r dash for this, 4 by 3 r dash cube into d, it is cancelled. This 2 is cancelled. Here we get r dash is equal to n to the power 1 by 3 r. This is the relation between the final radius and the radius of one small drop. And charges are always conserved. So, for this, total charge will remain unchanged. This is final and this is the charge on each drop. For potential, you know the formula 1 by 4 pi epsilon, or in CGS system, you could simply write potential is given for a sphere by the relation Q by R. For the big sphere, it's going to be Q dash upon R dash. Q dash is NQ and R dash is here n to the power 1 by 3 into R. So it becomes n to the power 2 by 3 V. Potential becomes n to the power 2 by 3 into V. Q, radius, charge. Capacity is depending simply on R. So C dash is also, you might say, given by this relation, capacity. C, Q, R, V. Then by using the relation half CV square, you can have the relation for potential energy that's given here n to the power 5 by 3 U. Potential, n to the power 2 by 3 V, and so on.